Welcome everyone. We'll continue to discuss our topic resource allocation and binding. So, just to recap what we have discussed in the last class, we found that in the high level synthesis, when the scheduling is over, that means we know which operation to be executed in which time stamp. The next step is to find out the resource or the hardware resource record, right? And specifically two type of resource you have to determine. The first one is the function unit, how many function unit you needed, and the second one is basically the storage, which to store the variables, right. So, the operations of the behavior will going to map to the function units, and the operators and the variables are going to map to the storage unit. So, we found that this particular resource allocation problem in general can be mapped to a click cover problem. So, what we can do, we basically we found that specifically for a few function unit allocation and binding, that if two operations are actually running in parallel, that means they are scheduled in the same time stamp, they are not compatible to each other. That means we need different kind of resource to execute these operations, right. So, by checking the compatibility of the operations, we can actually construct a graph where each node is basically a representing an operation, and then their edge represent the compatibility, and then we actually conclude that finding the clicks, the maximum click of that particular graph, or the number of click that is needed to cover all the nodes of the graph is nothing but the FU requirement, and each click represent one FU, and all the nodes within the click represent when can be mapped to that particular FU, right. So, that we have understood. Similarly, we have seen that the same problem of this resource sharing can be mapped to graph coloring problem. In the graph coloring problem, what we have seen that we can construct a similar kind of graph where each operations will represent a node, and then if two operations are conflicting to each other, that means they are actually executing the same time stamp. I am going to add an edge. So, then it will become a complete graph, and which is basically the complement graph of the compatibility graph. And then what we found that it is basically, if you just try to color the nodes of the graph, and then the nodes, if the nodes have the same color, they cannot be adjacent. If that is the logic we apply, then the minimum color needed to color all the nodes of the graph is nothing but the resource requirement, right. And each color represent an FU, and all the nodes have the same color actually can be mapped to the same FU in the hardware, right. So, that is something we understand is very interesting thing, that resource allocation and binding can be mapped to either click cover problem or graph coloring problem. Okay. And then just to give an example, that suppose we have this schedule like this, and then in the schedule, so there are 5 operations, and then the operation 1 and 2 schedule in timestamp 1, 3 and 4 operation is scheduling in timestamp 2, and 5 is scheduling in operation timestamp 3. So, we have to consider the operations of same type at a time, because we cannot map a multiplier and adder to the same FU, right. No point taking multiplier mapping and adder mapping together. So, we are going to consider the multiplication mapping once I have done the problem solved, and then we will go for the mapping of the adder and so on, right. So, here all the operations are ALU type operation, which is addition and subtraction. Okay. So, what is the conflict graph? It is basically, this is the conflict because operation 1 and 2 is executing the same timestamp. So, there is a conflict there, and then you have this operation 2 and 3 is happening, 3 and 4 is happening here. So, there is a conflict there, there is no other conflict, right. So, in this graph, if you try to color the nodes, I can give the color like this 3 node the same color, because 3 nodes are not adjacent to each other, and I can keep the same color. So, that is what I have shown here. So, this is basically my FU1, okay, and I can put the color green to this node and this node, and this is my FU2, right. And then this FU1 is going to execute the operation 1, 5 and 3, and FU2 is going to execute operation 2 and 4, right. So, this is the graph coloring problem, reduction of this resource allocation and binding to the graph coloring problem. Similarly, we can actually construct the compatibility graph. Here it is basically the edge represents the operation compatible to each other or not. We can see here the operation 1, it is compatible to operation 3, 4 and 5, because they are running in different timestamps. So, from 1 I have it edge to 3, 5 and 4. Similarly, operation 2 is compatible to operation 3, 4 and 5. So, 3, 4, 3 and 5. This way I can actually construct this graph, and then if there is a click, this is a complete subgraph, I can found a complete subgraph of 1, 3 and 5. You can see there is a complete subgraph here. So, that means these all nodes are compatible to each other and they can be mapped to a single FU, and that is a maximal clique. So, I found a clique of 3 nodes, and again this is representing my FU 1, and then I found from the rest of the nodes I found another clique of 2 nodes, there is a edge between them. So, this is my second clique. So, there are 2 cliques which cover the whole compatibility graph, and one clique represent the FU 1, second clique represent the FU 2, and same I can see that the results are same in both cases, right. So, this is how we have discussed the problem can be mapped to either clique cover problem or graph coloring problem. Then we found that in general the problem of this graph coloring or clique cover problem is basically NP complete. That means, we do not have efficient algorithm, that means deterministic polynomial time algorithm to execute the problem in So, usually we go for heuristic algorithm. Then we discuss that for a specific set of graphs, specific class of problem, this problem is actually polynomial time solvable, and we found that if that conflict graph is basically chordal, that means if you have in the conflict graph, if there is a edge cycle of at least 4 nodes, then always you have a edge, a chord, right. So, this is a cycle of 4 nodes, we have a chord there, right. So, if that particular conflict graph is chordal, and then we found that there is another subset of the chordal graph is basically interval graph. So, which says that if we can map this node of this in conflict graph into some intervals such that if there is an edge between these two this node, so then their interval will overlap. So, for example, here 1 and 2, I just map them into this interval, and then I show that this is because there is a edge from 1 and 2, they will overlap. So, if I can map all these nodes to such interval such that whenever there is an edge, the corresponding intervals will overlap, then I can tell this particular graph is interval graph. And then we have, what is the advantage of this, that we found that if that conflict graph is an interval graph, and actually I can solve the problem in polynomial time. Okay. So, in general, so what we actually found that by this Gilmore theorem, that if my conflict graph is an interval graph, if and only if it is a chordal graph, and its complement graph is comparativity graph, right. So, comparativity graph in the sense that so it has a transitive orientation, right. So, although this conflict graph is or comparativity graph is undirected graph, I can actually add a direction of the edges, so that I can make this particular graph as an undirected graph to directed graph, and then whenever there is an edge from I to j and j to k, then I have an edge from I to k. So, the transitive property holds by these transitive orientations, right. Then I will say that particular graph is comparativity graph, and we found that if one graph is interval graph, if and only if that graph is basically chordal, that means it has chord, and its complement graph is comparativity graph, that means it has transitive orientations, right. So, the conclusion of this discussion is, if I found a particular graph, an interval graph, then I have a efficient algorithm, right, polynomial time algorithm. And to identify a graph is interval graph or not, I have to apply this theorem. I have to check whether that particular graph is chordal graph or not, and its complement graph is comparativity graph or not, right. If it is that, then it is an interval graph, and if it is an interval graph, I have a efficient algorithm which I can apply to solve this graph coloring problem. Okay. So, then we discussed that if we take only one basic block at a time, right, because during scheduling we discuss most of the time that you take one basic block of the whole code at a time, and then try to schedule that, and then you combine the all schedule together to get the the overall schedule, right. So, now if you try to solve this resource sharing allocation problem for a particular block or a particular basic block, then this particular problem is actually a polynomial time solvable. Specifically, that conflict graph, if we construct the conflict graph for a particular basic block, then that particular graph will be chordal graph, and then its compatibility graph, which is the complement graph of the conflict graph, which is comparability graph, right. So, that means, if we try to solve the problem of resource allocation and binding for a specific basic block, I can solve it easily, and we have discussed that we can actually apply this left edge algorithm for that to solve this problem. Okay. So, we are going to discuss this left edge algorithm in this class in detail. So, but before that I try to show you that what is the interval graph looks like for a basic block, right. So, if you consider this is the operations in happening in one basic block, In the basic block means there is no control flow, there is no loop, it is a sequence of operations, right, and this is the corresponding schedule that I have obtained from scheduling, and then wherever the operation is scheduled, that is the interval, right. So, this is the interval of this operation. So, this is the interval of operation 1 and 2, this is the interval of operation 10 and so on. So, now I can consider this is the intervals, and you can see here because this 1 and 2 is conflicting to each other and their intervals is overlapping, right. 1 and 3 is not conflicting to each other, their intervals are not overlapping, right. So, this way I can actually show that this is the corresponding intervals corresponding to given this schedule, and if I construct the conflict graph here, say for multipliers. So, this is my 1, this is 2 and say this is 3 and this is 6, because I have only 6 multiplier 3 and 6 and 7 and 8, rest of the operations are ALU, I am not going to consider them, and then say 7 and 8. So, 1 and 2 is conflicting, 3 and 6 is conflicting and 7 and 8 is conflicting. Obviously, it is a chordal graph because there is no chord or there is no loop, and then we can see here is that this 1 and 2 is have a conflict. So, their intervals is overlapping, 3 and 6 has a conflict. So, their interval is overlapping, 7 and 8 is conflicting. So, their intervals is overlapping. Okay. So, this is how I can actually get the intervals, right. For a given schedule, I can actually identify the intervals of each operations based on their schedule. One, it may be noted that if one operation is scheduled for multiple cycle, its interval will be over more than one cycle. Okay. So, this is how I will get the intervals of that node, and then I will move to the left edge algorithm. In the left edge algorithm, as the it suggests, it actually can solve this problem in polynomial time. What is the problem? Graph coloring problem. So, what is the input to my algorithm? We have a complete graph and hence the intervals, right. So, because I know what is the interval corresponding to the schedule. So, I have both this complete graph as well as the intervals, but this particular algorithm takes the interval as an input. Okay. So, I have given the set of intervals, and what it will return? It will give you set of colors, right. So, it will give you set of colors, say 3 colors or 4 colors, and also mapping of each node or each interval to that color. So, that means if I know that interval 1, 5 and 7 is have the color red, that means 1, 5 and 7 is going to be executed using same FU. Okay. So, so it solved the graph coloring problem on the intervals given. Okay. Now, the question is how I am going to represent the intervals, right. So, the intervals are represented for this algorithm as a left and right edge, right. So, if you see here, so if I just say this is my time, right. So, I now actually in for the previous example it was in the top to bottom direction, now I am going to make it left to right direction, you can always rotate it, right. So, now I can say that this is my intervals, this is interval 1, 2, 3, 4 and so on, and this is how I am going to represent the intervals, right. And say every intervals can be represented by two things, right. It is left edge and the right edge. So, this is L I interval I L and this is I R, right. So, I can represent an interval I by I of L and I of R, right. So, this is how I can represent an interval. So, given the intervals, I will represent the interval by the coordinates of their left edge and right edge. Okay. So, interval of, for example, for this particular edge, this is equal to 1 and it will be always complete. So, this is basically I r equal to 4. For this, it is basically the interval is it will be complete, right. So, this I L equal to 1 and this is I r equal to 2, right. So, this is the interval. So, now what this algorithm does apparently? It first sort this interval based on their left edge, right, as the name suggests. So, it actually sort these intervals based on their left edge. Okay. It first does that. So, let us take an example first. Suppose this is my intervals given and you see here this is the sorted order, right. So, given these intervals this is the sort. So, this is my complete graph and say this is the corresponding interval because I have this the inputs. So, I have sorted the things, the sorting order is 1, then 6, then 4, then 7, then 2, then 3, then 5. You can see this is the sorting order of this interval based on their left edge. Okay. So, now what this algorithm does? It takes a color 1, right. So, it takes color 1 and it scan this list from left to right and identify the first node. So, initially you can assume that none of the interval is selected. So, what I am going to do? I am going to select the first interval from this list which left is not overlapping with the previously selected one, right. So, if you take the first iteration, I can assume that the previously selected one is -1. So, I can select 1, right. I can select this 1 because it previously selected was none. So, I can assume that right edge is -1. So, I will say that this particular I am going to select this 1 because it is not overlapping with the previously selected interval. Okay. So, I have selected 1, then my now current selected one is 1. Now, I will go to the next one and will see whether that particular interval the left edge has a overlap with the previously selected one or not, right. So, how can I check that? If the left edge is greater than of the right edge of that previously selected one, right. Since here the left edge of 1 is not less than of the left edge of 6 is not greater than of 3 of the previously selected one, I am not going to select 6 in this iteration. I cannot select 4 for the same reason. I cannot select 7 because same iteration, because the left edge of 7 is not greater than of right edge of 1, right. So, I am not going to select, but I can select 2 because the left edge of 2 is greater than equal to the right edge of the previously selected one. So, I am going to select 2 as well. So, I have selected 1, I have selected 2. Once I select 2, I can I go to the next one, it is 3, and I can select 3 because the left edge of 3 is greater than equal to of right edge of 2. So, I have selected this one, I have selected this one, I have selected this one. So, these 3 if I select, once I select 3, I cannot select 5. So, this is the 3 node which I can put color 1 and they have non overlapping interval. So, that means they can be mapped to the same APU, right. This is how every iteration it scan the list and identify the intervals that can given the same color. Okay. Once these 3 are selected, I will remove them from the list. Okay. So, the same process is going to execute for the remaining iteration. So, now I will select the color 2 and I am going to select the color 2, I will select 6 because this is the first one, I select 6, and then once I select 6, I cannot select 4, I can select 7 because 7 left edge is greater than equal to of the right edge of the 6. So, I can select 7 and then once I select 7, so this is C2, this is C2, I can select also 5, right. So, you can understand that. So, I am actually assigning color 2 to 6, 7 and 5, and then the next iteration only one is left 4. So, color 3 will be assigned to 4. So, this is how every iteration it try to find out the maximum number of possible intervals that can given the same color, right. And this is how I can solve this problem, and here it is the way I just discussed that 1, 2 and 3 schedule in when given the color 1 and then of 6, 7 and 5 is given the color 2 and 4 is color 3. So, 3 color needed and operation. So, if you just look into this. So, now I just take the concrete graph. So, that means 1, 2 and 3 has the color yellow and say this 6, 7 and 5 has the color say orange and this 4 has the color purple. You can see here that no two adjacent node has the same color, that is the rule of graph coloring, right. So, I am going to give the color to the node such that no two adjacent node has the same color, and that actually gets satisfied here, and hence I need 3 color to solve this problem. Okay. And also mapping of the each of the node or the operation to the FU also is determined by the left edge algorithm. Okay. So, I will just formally explain the algorithm. So, it takes the intervals I which is given by the left edge and right edge, and then I am going to sort the intervals based on the left edge, not by the right edge, it is by the left edge. So, you can see here it is already sorted by the left edge. Okay. And then what I am going to do? I am going to take one color at a time. Initially say my color is say C0. So, then this outer loop will execute until all the intervals are get over, and then every iteration of this inside I am going to find out the nodes that can be given that particular color, right. So, now this particular while loop identify all the intervals that can be given the same color, and that is given by this logic, right. So, this is greater than equal to that I am going to select the next one whenever my the IS, that left edge of that is greater than equal to the R is the previously selected one right edge. Okay. So, once I found something, I will find that particular node and then I will put into the list. So, all the nodes initially put into S can be given the same color, initially S contain phi, right. So, there is no element there. So, gradually and initially my right edge is 0 because I am starting from 1. Okay. So, then I select the element, I put into the list and then I make my R equal to R s, the right edge of the currently selected one, that the way I discussed in the previous one, right. And then I delete S from L because it is already selected. So, this way this one iteration of this loop will identify all the intervals that can be given the color C, current color C, right, and then I increment the color and basically I giving the color 1, 2, 3 and all. So, I am giving the color and then I will go for the next iteration and that will go for color 2 and so on, right. This is how the whole algorithm works. I hope you understand. So, what is the complexity? Let us understand that. So, sorting of n numbers. So, let us say the number of nodes is n. So, which is basically order of n log n, right. That is the most efficient comparison by sorting algorithm we can apply. And then there are two loops, right. So, looks like kind of n square, but let us understand the amortized cost of this. So, what is happening here? So, it has the list of node. So, this internal node will scan the whole list at a time, right, and then the list has n number of nodes. So, it will actually identify all the intervals that is got selected, right. So, that I am going to select here and then next iteration those nodes get deleted, right. So, the next iteration I am going to select only the rest of the intervals available, right. So, this is how the whole thing works, and you can actually understand that if we actually do a amortized analysis of this, it is basically just scanning the list for few times, right. So, it is basically the number of color that you identify, that is the number of time you are going to scan the whole list, and every iteration the list get reduced, right. So, the overall complexity of this will be order of n. So, the overall complexity is order of n log n, right. So, where I am assuming the n is the number of nodes in the conflict graph or the number of intervals available to me. Okay. So, so that is why the complexity is n log n, and it is specifically because of the sorting of the intervals. Okay. So, now let us take the example that I talked previously, that this is the schedule, and this for this schedule I have this is the interval. I am going to consider only the multiplier, and then you can consider the ALU operation in the next iteration, right. So, here the intervals are actually given in this order. So, you can assume that this is your left edge, this is the left edge and this is the right edge. Okay. This is the left edge and this is the right edge. So, what will be the sorting of this? It is 1, 2, 3, 6, 7 and 8, right. So, now you take the color 1. So, I can select 1. If I select 1, I cannot select 2 because they are overlapping, and then but I can select 3, right, because 3 the left edge is greater than equal to the right edge of the previously selected one. So, I can select 3. So, I am selected 1, I selected 3. Once I select 3, I cannot select 6, but I can select 7, right. So, I am going to select 7 because it is non overlapping with 3. So, that means in the first iteration I select 1, 3 and 7, and which is given the color 1, right, and then I will make it color 2. Then I will again scan the list, which I only have 3 elements now. So, I will select 2, right. So, I am going to select 2, and when once I select 2, I can select 3 also, I can select 6, and once I select 6, I can also select 8 because they are overlapping, right. So, this is the second color. So, by this way I colored these nodes, and then I found that I need only 2 colors to execute, and which is quite natural, that because you have maximum 2 operation executing here, 2 operation executing in this clock, 2 operation is executing what. So, that means maximum clock color requirement is 2, that is quite obvious from the schedule, but what is the mapping, that also it gives that color 1, that 1, 3 and 7 you execute in timestamp, I mean using the FU1, and 2, 6 and 8 you execute using the FU2. So, that means 1, 3 and 7, these 3 operation is going to map to FU1, 2, 6 and 8, this 3 operation is going to map to FU2, right. Okay. So, this is how it works, and this is how I can actually identify the FU requirement and their binding, allocation of the FUs and the binding of the FUs. Okay, both can be determined. One more example is given here, I quickly cover. So, suppose this is the complete graph I found somewhere. You can see here there is a cycle of 4 nodes and there is a chord, and there is a cycle of 5 nodes and there is a chord, right. So, that means this is a chordal graph, because this is a requirement that your complete graph must be chordal graph, and say suppose this is one of the possible mapping of these nodes to the intervals. Okay. And what is the first step? You sort them, and it is already sorted, you can see here based on the left edge. And then what I am going to do? I am going to add color. So, for color 1 I select 1, once I select 1 I cannot select 6 and 4, I can select 2 and then select 3. I think this is the same algorithm that I covered in the previous example. So, you can understand that 1, 2 and 3 3 can be mapped to color 1, and then 6, 7 and 5, which is non overlapping, can be mapped to color 2, and 4 can be mapped to color 3, right. And this is what is the color given, right. So, this is how I can solve the problem, and with this I conclude this discussion on left edge algorithm. Thank you.